Hello. We'll talk today about what is a logical statement and or logical proposition. You can find both in different books. And what is its negation and different operations between logical statements. So if you take like a sentence, like it's raining, it is a statement, it is a proposition. It can be true or it can be false. So I'll denote P, my statement. If it's false, I write a 0 here. And if it's true, I write a 1. This is called a truth table. And if I want to write the truth table of the negation of my proposition, it will be like if P is it's raining, or it can be, for example, if you want a math example, my statement can be ABCD is a rectangle. The negation of this will be ABCD is not a rectangle. And the notation for the negation of a proposition is not P. So you can find this symbol for not. So this is about negation. Sometimes you can find P with a bar over it, or you can find not P sometimes. It depends on the books, right? So if I want to build the truth table of the negation of P, when P is false, then not P is true. And when P is true, then not P is false. Because this means, like, for example, ABCD is a rectangle, then if this is ABCD is a rectangle, and the negation would be ABCD is not a rectangle. You have to understand here that formal logic, what we are studying in this little chapter, is about the validity of a proposition. But it's not about the truth of it. I don't know anything about ABCD for the moment. I don't know if it's a rectangle or not. I just look at what happens if it's true and what happens if it's false, right? So when this is false, 0 is for false, the negation of it is true. When this is true, it's a rectangle. The negation of it, it's not a rectangle, is false, right? So that's called a truth table. The main logical operators are a conjunction between two propositions. A conjunction means and it's denoted like that. So here is the truth table for the conjunction. Sorry, I'll take two statements. The first one is P, the second one is Q. And here will be P and Q. When I'm building my truth table, I need to be sure that I list here every possibility. So the best is to start always the same way. 0, 0, 1, 1. It's kind of an alphabetical order. So what I want every possibility with this true or false and this one true or false. So either P is false and Q is false, or P is false and Q is true, or P is true and Q is false, or P is true and Q is true. So every time you have two propositions like that, try to write the zeros and ones in the same order, It will help you compare different truth tables. In math, and is related to the intersection of sets, right? So, and is just like in the ordinary language. So if P is false and Q is false, then P and Q is false. For example, if P is I have socks on, and Q is I have shoes on. Here I have no socks and no shoes. And the conjunction would be I have socks and shoes on. I will put mathematical examples in the exercises. So here I have no socks, but I have shoes. The statement I have socks and shoes is false. It's so obvious when you take ordinary examples. Here I have socks, it's true, but I have no shoes. So the statement I have socks and shoes is false. Here I have socks and I have shoes, both are true. So the statement I have socks and shoes is true. This is the truth table of a conjunction. Could be the set of people who have socks and the set of people who have shoes on, and the ones who have socks and shoes are here. This is for the conjunction. Now, disjunction it means or. I said it in the previous course that previous lesson that or in math means or and. When you say in math, when you say that you can have cheese or dessert, it means you can have cheese or you can have dessert or you can have both, right? Let's keep that example. So P will be I have cheese. Q will be I have dessert. And P or Q is I have cheese or dessert or both. I list all the possibilities of P and Q being true or false in exactly the same order as I did here. So I can compare both tables at the end. Here, I have no cheese and no dessert. I have cheese or dessert is false. Here, I have no cheese, but I have dessert. I have cheese or dessert is true because I had dessert. I have cheese and I have no dessert. The statement I have cheese or dessert is true because I had cheese. Here I have cheese and dessert, and the statement I have cheese or dessert because we are in math is true because you have the right to have both. This is the truth table of a disjunction. Now, what is a conditional? A conditional is if then. If then. So P, Q, if P, then Q. This will be, it's sunny. And this will be, I go for a walk. So this will be, if it's sunny, then I'll go for a walk. Let's see what happens here. This is a little bit more difficult. So I'll keep the same order in my zeros and ones in order to be able to compare it to the other truth tables. So here, you have to understand that when I say, if it's sunny, then I'll go for a walk. It's a promise. I promise that if it's sunny, then I will go outside for a walk, right? So here, so the question is my promise true or did I lie? Did I lie to you? Here, it is sunny and I don't go for a walk. So clearly I lied to you, right? It is sunny and I didn't go outside. Here, it's sunny and I go for a walk. So I kept my promise. And the problem is here. What happens when it is not sunny? Well, when it's not sunny, the fact is I didn't promise anything. So your mind will want to consider that if I say, if it's sunny, then I'll go for a walk, means that if it's raining, I don't go outside, except it is not what I said. I said, if it's sunny, then I will go. But if it's not sunny, I didn't promise anything to you. So if it's not sunny, I did keep my promise because I didn't promise anything for the rainy days, right? This is very important. When you have a conditional statement like that, the whole statement, your promise, is true if the first one is false. And it is not easy to understand, right? Because your mind wants everything, as any human mind, to be biconditionals. Biconditionals is like Pythagoras theorem. You know, it's the main example of biconditional that everybody knows about. A biconditional is when both statements P and Q are true at the same time. So it's an if and only if. It's an equivalence. Like your triangle is rectangle and Q will be h squared is equal to a squared plus b squared. It's if and only if. If it's a right angle triangle, then this equality is true. And if this equality is true, then the triangle is a rectangle. You have an equivalence there. A biconditional means that P and Q are true at the same time. So I'll keep the same order as usual for the truth table. And here, they are false at the same time. So my biconditional is true. One is false and the other true, so my biconditional is false. Same thing here. And here both are true at the same time, so my biconditional is true, right? What is now, so these are the main operations you can do with two statements. Operations or relations. So what is a formal equivalence? A formal equivalence is when you find the same truth table for both of the things you are comparing. First example, I would like you to check the converse of a conditional proposition. So I'll have a proposition P, a proposition Q, a conditional P implies Q, and the converse of it will be if Q, then P. Same thing as usual. So I'll ask you to pause the video and to try to fill in those two columns. Pause the video now and try to do it alone. Then I'll do it. So I'll give the solution in 3, 2, 1. Let's do this. The conditional, you didn't have to do it again because you had it here. It's just the same, 1, 1, 0, 1. But you had to think a little bit more about the converse of it. So the converse, so when we said that this is a conditional, except it's the converse of this one. We exchanged a P and Q, okay? So when Q is false, like when the first here is false, then the whole statement is true. So if Q is false, which is here and here, then this statement is true, right? And then I have to see here Q is true and P is false, so this statement is false. And here Q is true and P is false, so this statement is true. What you can notice here is that these truth tables here are not the same. So a conditional and its converse are not equivalent. It is not equivalent to say, if it's sunny, then I'll go for a walk. And to say, if I go for a walk, then it will be sunny, because you are not God. You can't decide on the climate, right? Or the weather. It is not, most of the conditionals are not equivalences. It means in most of the cases, your conditional won't, the converse of your conditional won't be true when your conditional is true. Now, we'll check the contrapositive of a conditional. Sorry, wrong color. This will be asked at your exam, probably, because it's part of your program. So let P and Q be two prepositions. So I have this conditional and the contrapositive of this. The contrapositive of this is if not Q, then not P. So if it's sunny, then I'll go for a walk. Sorry about my ugly drawings. The contrapositive would be if I don't go for a walk, then it means that it's not sunny. Okay? So we'll try to build the truth table of this and see what happens. So we'll write P, Q. If P, then Q. This is your conditional. Then the truth table of not Q, truth table of not P, and truth table of if not Q, then not P. I'll let you do it. You post the video and I'll give the solution afterwards. Solution in 3, 2, 1, go. So this is P, same order as usual. This is Q. P implies Q. If P, then Q. We have already done it a lot of times. If I want to fill in this column, it's not Q. It means when Q is false, this is true. When Q is true, this is false. When Q is false, this is true. When Q is true, this is false. Same thing for not P. When P is false, not P is true. When P is false, not P is true. When P is true, not P is false. When P is true, not P is false. So I'll just look at this to build this here, okay? We said that when not Q is false, the implication here, the conditional is true, right? Because I didn't promise anything for when this is false. So when this is false, this is true. Okay, now, this is true. This is true. And this is false. It means I lied. Like this is true. And this is false. It means this, the whole statement here is false. This is true and this is true. It means this is true. What do I notice here is that I get the same truth table for this and for this, which means it's very important. This is very important. It means that a conditional and its contrapositive are formally equivalent. This is very useful in exercises because most of the exercises are conditionals like that. So the exercise wants you to prove this. And if it's too difficult, if you can't prove this, you can just prove this instead because it's equivalent. If you prove this, then this is proved too. It's the same. It's if this is true, then this is true. They are equivalent. They are true at the same time. So if you can't prove this, try and prove this one. Sometimes it's really easier. I'll give examples in the exercises. Last two things. There are two exceptions or two special statements. What is a tautology? A tautology is a statement that is always true. It's always true. Like 1 is equal to 1 or blue is blue. And a contradiction is something that is always false. So its truth value is always 0. It's like 1 is equal to 0 or things like that, right? This is a contradiction. Tautology is always true, contradiction always false. And that's all for this part.